So now we're on to testing. Basically, how do we know that these things are going to perform in the field? It's very easy to do some testing and feel calm. Okay, that's great. We know this is going to pass. It's a whole nother thing to know that when this leaves, they're going to perform forever. And so let's talk a little bit about that team and what they bring to the table and how they do their jobs. So the testing process consists of a number of things, from optics to mechanical testing, so impact and recoil testing. Then we need to look at environmental testing, and throughout all of that, we have to make sure that the function testing, so adjustments turn, power selectors move like they're supposed to. And so let's dive into each of those a little bit. The optical testing starts with it's a really neat room. So there's a lot of it. Our main testing area for optical performance is it's just down the hall here, and we're close to a neighboring highway. So Highway 26 goes by us. There's a lot of truck traffic, logging activity, et cetera, that goes by pretty close to our office. Everything in that office is on an air ride suspension, and that's set up so that we don't have any vibration coming into an optical platform or a full system while we're doing the test. This room, as a matter of fact, will be locked and closed with the lights out while we're doing some of our testing, because the additional heat of having one person in the room can impact the test results on something as non-related as you might think as light transmission. So extra heat in there can affect the temperature of the air and then affect the testing results that you see on light transmission in certain areas of the visible spectrum. So this lab is the very first place that we have to go, and we can get into depth on glare, light transmission, surface irregularities on any lenses, really making sure that when we mount all of this stuff up in the optical prescription that we know exactly how that's going to perform. So with optical testing, there's a number of the things that we automatically think about. So the glare, the resolution, each of those items. What I'd like to dive into a little bit farther is something that not as many people might think about. When you have this optical prescription set up and you can zoom from say 5 to 25 and you can adjust your parallax from say 20 yards all the way out to a mile and beyond, there's moving pieces in there. But the fixed pieces are also equally critical. And the reason I say that is because those fixed pieces, all the different lenses that are in there, they create the magnification that you see. And that is extremely important to get very, very precise. Let me give you an example. So if you look at reticles, if you're going to hold over with a reticle or hold for wind with a reticle, so a grid style or even just a basic mill or TMOA type of a reticle, when you look at the different lens elements in there, the effective focal length of a scope is the true measure of magnification. And that number may be up somewhere around 600. If it's off by as little as 1% on the total magnification throughout the entire scope, you're going to have that much error on how far you hold off with your reticle. Or, as strange as this may seem, how far it moves when you turn your dial. And so we really need to make sure that all the magnification is coming out exactly as prescribed, the way that we thought, so that when we make the adjustments and create the appropriate thread pitches for the adjustments, and then the markings on the reticle themselves, that all of those match exactly to the magnification that you're really getting out of that scope. Then we want to go test how well does it hold that? How well are we going to retain all of those values throughout a whole myriad of environmental changes? We go through and we have chambers that will take the scopes down well below 0 in Fahrenheit and will hold them there. We also have the same chamber can take it well up above 120, 140 degrees if necessary and hold them there. One of the big things that will affect the potential performance of an optic is cycling back and forth. So we also test that. We will take it cold, we'll take it warm, we'll take it back and forth. And what ends up happening there is you're basically inducing a thermal shock to the scope. As hunters, we see that, where you may be in a nice warm tent and then it's time to go outside and it's below 0. Or you're riding around in a warm vehicle and you get out. Or vice versa, where you can come in from the cold, step into a nice warm tent where there's a fire going and you're going to shock those systems. As we all know, that's why scopes need to be fog-proof. That's why we fill them with a gas to keep them from fogging up on the inside during a big temperature change. So we simulate that right here on site. And so these scopes will go into an extreme cold environment. We'll take them out. We'll try to shoot them if we can at certain times. But as you may recognize, when you take an optic out of a very cold environment, let's just say 0 degrees, when it comes out of that, it hits the moisture in the air and it frosts over. And so this is the type of testing that we need to do. Does everything still want to turn? Does it still want to move? Can you make the adjustments that you need to? We do the same with warm temperature. You don't have as much of a fogging issue there, but you do need to make sure that it's going to operate. You go to a PRS match, set your rifle down. It's not uncommon for the sun to be hitting the rifle, the stock, the barrel, etc., and warm these things up well over 120 degrees. You know, they're hot to the touch. We have to test all of that and make sure that everything retains function. We've all seen things expand and contract as they get warmer and they get colder. Everything in the scope needs to remain sealed. So as these scopes are subjected to, say, heat, everything wants to expand, and that gives the opportunity for the gas to escape. If everything expands, it's not sealed up as tight anymore. The gas may escape from inside of the scope, basically breaking that seal. And now the next time that you go somewhere cool and then into the warm, it may fog up. That humidity change can give you an internal fogging in the scope, and you never even knew that was coming. Great example of this. I mean, people aren't always jumping out of airplanes with these things, but people fly to go to hunting camp, or they fly to get wherever they're going. The cargo hold in an airplane, I don't know if you've ever looked at the temperature outside when you're flying at 30,000 feet or 40,000 feet. It may be 70 below zero. Now they do climate control a lot of the cargo hold, but that is something that we see. There's a pressure change when you go up that high, and there's a temperature change. And if you have not tested appropriately for this, simply flying to Alaska to go on a hunt could cause your scope to break. You know, the seals are no longer sealed up, and you get there and now it fogs, and you know that warranty doesn't do you a whole lot of good on a mountaintop somewhere where FedEx won't come get you. So we need to make sure that these things are going to work regardless of what they are subjected to. We also simulate tests for things like chemical. So these are going to be subjected to various types of chemicals, from cleaning solvents to lubricants and other things that just in daily gun function. You need to clean rifles, you use solvents. So we subject them to all the common chemical tests that you may run into out there. And some of them would surprise you. The gun cleaning agents are pretty harsh chemicals, and they can have negative reactions with things like rubber O-rings or seals or finishes. And so as part of the design, we need to make sure that A, they can withstand that, and then B, we test to make sure that they will continue to perform regardless of the chemical exposure that they may see. Altitude or pressure is another one. So we all know that pressure changes can affect the performance of the bullet, the flight path of a bullet. It's different at high elevation than it is at sea level. Scopes go through lots of pressure change, whether they're on an airplane or just hiking up and down a mountain, and we simulate that in pressure chambers. So we can draw a vacuum and simulate a lower pressure. We can basically pump air into these and simulate a higher pressure, and we test to levels far outside of what you'll see in an environmental setup. The lifetime use thing is a challenge. How do we know how often someone's going to shoot? How do we know how often they're going to make an adjustment up, down, left, and right? How often are they going to turn the power selector ring? The answer is we do surveys and tests, and we look at that, and then we put in a very large safety factor. We test these far more than people will ever use them. The odds of the average person turning this power selector nearly as often as we do in our testing with a little motorized tool that turns it back and forth and checks for function, you're not going to get there. But what that does is that helps us know that for any user out there, they're not going to wear out some of these components. It's got a lifetime warranty, it's got an expectation of functioning forever, and so we test it to make sure that it will. And finally, after we've gone through and tested all of these other things, now we get to the biggest barrier, the biggest obstacle, if you will. And so this testing is really what allows the design team, the production team, all of us to know that this new product is going to survive forever. And that's really the recoil testing. And the reason that that is such a critical thing is that when we go through and do the recoil testing, we then go back and do all the other testing all over again. So after this is subjected to multiple lifetimes of shooting, that impact or recoil, it still has to be resistant to all the solvents, even though things would try to loosen up under recoil or whatever. It still needs to remain sealed and waterproof and fog-proof at cold temperatures and warm temperatures. We need to pass all of those tests again and throughout the impact testing cycle. So what we'll do is we'll take and we have a machine downstairs that simulates recoil and can replicate the exact recoil of virtually any firearm out there. So we have a baseline test. We know that it represents average hunters, shooters, etc. very well. It actually supersedes what anybody will typically ever shoot with in terms of the heavy recoil, the G forces that you'll feel. And we do that for thousands and thousands and thousands of hits. What that does is that tells us how this scope is going to perform after the first shot, after a series of shots in the middle, all the way down to the very last one that we test to. We check, is it holding the same point of impact the whole time? And we can tell down to like 100,000th or a thousandth of an MOA. Is it still sealed? All those other tests. We do that periodically throughout the entire impact testing cycle, because you as a shooter or you as a hunter, you need all of those features, all of those performance characteristics after every single shot. You never know which one's going to be the one that counts. A lot of people don't realize that recoil is actually kind of a three-dimensional force. And so people think of recoil as when you pull the trigger on, let's say it's a handgun or a rifle, it comes back, right? So really what happens to the optic is the optic tries to go forward. The gun tries to come out from underneath it. So we think of that as kind of an inline impact. So you could drop it and that would simulate recoil and you could test it that way. It is a lot more complicated and a lot more challenging than that. If you think about a rifle, when you pull that trigger, the rifle comes back, it also comes up, but what is the bullet doing when it goes down the barrel? The barrel is a spiral, right? And so that makes the bullet come out spiraling. That also creates a torque effect when you pull the trigger. And so the recoil that the scope feels is actually three-dimensional. It is forward, the gun comes back, but the scope tries to go forward, the gun goes up, so the scope tries to go down, and the whole gun is twisting. You don't notice that as much on a rifle, but you may feel it on a handgun. And so we need to test to that three-dimensional recoil impulse and really make sure that things are going to hold together. What you won't get by doing an inline drop test, which is the way that some folks choose to do it, you won't notice that things try to unscrew themselves. So there is a torque every time you pull the trigger, and after you do that several thousand times, something may try to come loose. A lot of these scopes, a lot of the components are actually screwed together and then there's an adhesive put in there to keep them in place. But after a lifetime of trying to loosen them, they may come loose. That portion of the test is extremely critical to ensuring that these scopes will last you a lifetime. In addition to the three-dimensional component of recoil, there's also a duration component. And so let me explain that a little bit. We hear people talk about, say, 50 BMGs. This will withstand X number of shots on a 50 BMG guaranteed. The duration, for those of you that have fired a 50 BMG or other cartridges, you may notice that recoil feels a lot different than, say, a 30-378 Weatherby, something that is a very high-speed bullet coming out of there. The scope feels it differently as well. So there's a duration component of recoil. And I can come up and push on something, and I'm much less likely to break it than if I jab it quick with the same amount of force or even less force. And so that duration is really a key ingredient, a key component. Our machine, which we call the Punisher, simulates real recoil from a firearm that we've tested downstairs. And that trace, our baseline trace that we use when we're testing things on the Punisher, will break optics, and we test them all, much faster than, say, a 50 BMG would, and the main component is that duration. And so the faster and the sharper the recoil is, the more likely it is to jar something and cause a problem down the line. So we tend to use the most harsh, the most difficult set of test parameters to pass, and we apply that to every single optic we make. And handgun recoil is actually a completely different critter in itself again. So if you think about a handgun, the cartridges are smaller, but so is the platform. And so when you're firing a handgun, you've got a couple things happening. There's a lot more torque happening, so the firearm itself moves a lot farther, but you've also got the slide coming back and stopping. So if it's a semi-automatic, the slide starts, it comes back, and then it hits a hard stop on the back, and everything rotates. The actual G-forces that something small like a reflex sight that goes on a handgun, or even a magnified optic that goes on a revolver, the G-forces that those optics feel may be 3 times higher, maybe 5 times higher than what you would feel on a rifle. And so this type of an optic needs to go through kind of handgun testing. And we've got another program for that. If we think something's going to be used on a handgun, we test for a completely different recoil signature yet again. And that is absolutely critical for anything that will go on to those smaller, lighter firearms. Once we've gotten a design all the way through the environmental testing, the impact testing, the chemical testing, pressure changes, all of those things to where we know it will perform in the field, we also need to make sure that it's going to perform on its way to get to the field. So that may consist of packaging drop testing. So we put everything together. That scope needs to make it from our factory onto a truck and off to either a distribution center or a store, or it could be a storage facility somewhere that's not climate controlled. And there's a lot of things that can happen in between there. And then once it gets there, there's more things that could happen. So we do a lot of testing for just standard dropping, rough handling, vibration, etc. All of that is part of the kind of the final testing we do once we know the design is sound. But there's one last component, and that is the kind of what I would call the human component. Once it's gone through all of this, if you're anything like me, it happens, you may drop it. It may fall out of a tree stand. You may be messing with something and it gets knocked over and lands on the concrete. We need to make sure that they're also going to survive those types of things. You're climbing up a mountain and you slip and you fall and the rifle and the scope hits first. Those things happen. That's a real life example of needing to make sure that the scope will perform regardless. And so we go through and do a series of drop testing as well. Just one example, mount the scope onto the type of firearm it would typically be mounted on, turn them upside down, drop them on concrete. So you have the weight of a fully loaded AR platform with full magazine, everything in it. It's simulated weight, by the way, for those that are watching for safety. And you may have something like this riding on the top of it and it lands first. That can and does happen. So we simulate all of those types of drop testing, whether it's directly onto the optic, if it's onto it at an angle, on a rifle, on a handgun, whatever that may be. We need to make sure that that human factor is also put in there, because it's just, we intend these to be used hard in the wildest places. They need to live up to that as well. So now we've gone through and we've found a consumer need. We've designed that consumer need and found a viable path forward. We need to now take this design and we need to start building it. It needs to go into production and run through our entire shop and come out on the other side, ready to go off to end users. Let's take a look at how that works.